So here you can see this is the entire buck converter setup. So this is actually interleaved buck converter. But what we have done is we have removed one leg of it. Okay. So we have removed one of the legs. So it will be working as a normal buck converter. All right. So from here you can see this is the microcontroller that we are using. Then there is a power supply for the gate driver circuit. 15 volt, because we need the 15-volt power supply to the gate driver, right? Then we have this load resistance. We have this voltage supply that we will be using to test this, and this is a CRO for seeing the waveforms. Yes, okay. So I will turn on.
Sir, your screen is not visible, sir.
Screen is not visible.
Yes, it's visible. Screen is visible.
Okay. So here you see this is the gate driver circuit. This small one. This one I'm. Yeah, this one, and there are two gate drivers actually, but one is non-functional because we are using this as a buck converter. This is actually interleaved buck converter. So from here, for this supply, we are giving it from this power supply module, which is fed from this transformer. There is a rectifier here, and it will down the voltage to 15 volts. Okay. From there, we are giving it to this gate driver circuit, and from the gate driver circuit, we are controlling this switches. From this side, you can see the switches, and yeah, uh, from here we will be supplying the voltage. So let me increase the voltage. Yes, I'm giving around 20 volts. So you can see on the multimeter that we are getting 10 volts output. Okay. So we are giving 20 volts as input, and we are getting 10 volts as output. So this is an open loop system. We have programmed the microcontroller to output 0.5 duty cycle, and yeah, it's this is how we can design a complete buck converter with this circuit. Now I'll show you how the PWM from the microcontroller. Okay. All right. So here you can see we are getting the pulse. So this is the pulse coming out from the microcontroller. Here you added this to this CRO, and you can see this is 50% duty cycle. So you are getting the exactly half voltage from the input side. And yeah, that's it for this demonstration. I will be heading to the PPT, and I can take any questions or queries you have.
Okay.
Hello.
So,
Hello.
Shashwat, I think your presentation over. Am I right?
Sir, one question.
Good morning, sir.
Shashwat, am I audible? Please unmute
Yes, sir.
yourself. Okay.
Yes, sir.
So, kindly conclude your presentation. Complete. Am I right?
Yes, sir. It's completed and
So,
thank you for your questions.
yes, yes. I'm requesting all the esteemed participants, if you are having any queries, please let us know. We are happy
Good
to
morning, sir.
respond.
Yes.
Good morning. Yes, thank you.
Nice presentation, sir. Sir,
you.
I'm having one doubt. Single layer PCB design or multi-layer, which one is preferable, sir?
Actually, multi-layer is preferable, but for multi-layer, we will have to go with PCB designing manufacturers, right? PCB design manufacturers like JLC PCB
Yeah.
and all. But let's say you are making a prototype that, so you'll be having many alterations. So you can every time you can send it to a PCB manufacturer. That will be not that won't be cost friendly and it will take many times because you will send,
Okay.
then they will reply. Yeah. So this is a single layer process. In this process, you can do it multi-layer because this copper cladded plate, it is only clad on one side. The other side is not conducting. Okay. So
Okay.
yeah, that's
Thank you, sir.
yeah.
Hello.
Yeah.
Hello. In a similar manner, we can design gate driver for any DC-DC converter, no?
Yeah. Sure.
Okay.
So
Okay.
not only gate driver, we can design any PCB that you want. Actually,
Power
there are many
circuit
things
as
in
well
this.
as control circuit. Yes.
Yeah, power
Both.
circuit as well as control circuits.
Both we can
Okay.
design.
Okay. Sir, what you have shown the sensor. Sensor we also can design in this.
Yeah, of course. This
Okay.
voltage and current sensor, you can design these circuits on in the this you can design the same way. This LV25P is also available in the KiCad. This IC.
Okay. Okay. Thank you.
Anything else?
Is there any other query? Any other queries? Please let us know.
Sir, I have a doubt,
Okay.
sir.
Yes,
Yeah.
yes.
Sir, you are designing an buck converter and then low side driver, sir. Actually, it is an you should have to design a high side driver, sir.
Sorry, I didn't
Because
get it.
the source is floating, na, sir.
Source is floating. Does that mean? I think I'm not aware of it.
Can you please elaborate your question? Means we are not able to get your question. Actually.
Yeah.
Hello.
Yeah.
Can you please elaborate your question? Hello. Where is it left? Please ask your question, madam. If you are having any doubt, please let us know. We have to start the next session. Till we schedule 11. We are going to
Can
conclude.
give us 5 or 10 minute break. Hello.
Yes, yes, we can give 5 minutes
Sir.
break. Okay, no issue.
Okay.
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 Please, we need to conclude it. If you are having any queries, please let us know. Some of the professor raised their hand, but didn't ask any question. Okay, then we're concluding the session. Thank you, Shashwat and Shivankar, because
Thank
session
you, sir.
was, I think session is very important. It was good, and I think all the participants learned a lot of things from the session. Okay. So,
Thank you.
yes, two participants raise your hand. Paul Matthew, please ask us what is your query. You have raised your hand, and Professor Madhumita Das Sharkar. Please raise your, you have, both of you raise your hand, but didn't ask the question. Please let us know. You're having a doubt, please let us know. Please unmute yourself and ask us.
Hello.
Yes.
Hello.
Hello, sir. My question is that the driver designed by you is an low side driver, sir.
Low side means, what is the meaning of the low side? I'm not able to get it.
The ground is connected to the source, sir.
How
If it
driver
is an,
is
your
already
source is
isolated.
actually, if it is a buck converter, your source is floating, sir. So the power supply ground should be shorter to the source.
Why floating? I'm not able to get
Yeah,
it.
on
Can you
TLP
please-
circuit, sir. Yes, sir.
The source is floating. No, it is isolated, right?
Isolated,
side is
no?
isolated
Power
from-
supply is
yeah.
there.
Sir, it is an isolated, but driver power supply should be shorted, sir. If you are using this circuit on an buck converter, sir.
Okay, sir, let me clear that out. Actually, you are right, sir. For a different other
Sir, if it is an
driver
high side
circuit that-
driver, you should have to use an
yeah,
bootstrap
I got
diode
your-
and bootstrap capacitor, sir.
yeah, I got your point. But we need the high side driver circuit for the buck converter as the switches are floating. I know, but in this case we are using a TLP 250, right? That is isolated from the input from the output. That is individually to act as a high side only. So you can use it. There are
Actually,
other
this is perfect
driver
for
circuit.
an buck converter. This driver is perfect for an buck converter. Sorry, boost converter.
Yeah, but it is isolated from the input to the output. So you can use for the single individual triggering circuit, you can use TLP 250 also. If you see the configuration of TLP 250, now it is isolated from the input and
It
output.
give an isolation from microcontroller and to the driver side, but the
See,
driver power
we are
supply should be
giving-
get shorted with the power converter supply. Okay, sir.
See, we are giving supply from the microcontroller to the driver circuit, and the driver circuit TLP 250 output side that will be connected to the switch, right? So the driver microcontroller side is isolated from the that switch side through the TLP 250. If you see the TLP 250 configuration, it will know. You can see the input is isolated from the output side. So for a single switching, you can use a TLP 250. If you use to use multiple switching, then there will be a problem. For a single buck converter, if you want to switch through the TLP 250, it is okay.
Are you getting your point?
Yes, may I ask one question? Actually, my mic is not working. That is why I raised hand, but I am not.
Oh.
Am I audible now?
Yes, ma'am, you are audible. Please carry on.
Yes, yes. Actually, my first question was the buck converter that you have designed for
Yes,
the for us for a specification with a specification, or it can be kind of general? You have
No,
started this for driving a voltage of 48 volt.
no, it's
Your load is what is your load actually? That is why you are converting this. That is
volts.
one of the most important thing that depending on that our buck converter specification, because you are using TLP, what is the maximum saturation voltage of that driver?
General viewer would take it. The
Madam,
main object is
I'm telling you
presentation
one
was-
point. Just Shashat, just 1 moment. Madam, okay, so
Yes.
driver, there is a power supply. Okay, so that will be your maximum saturation voltage. So maximum
Yes.
saturation voltage means you are giving some biasing voltage to your any of the IC.
It is okay, but that
Hmm.
what is that maximum saturation? What is the power supply of TLP?
That is plus
250?
minus 15. No? This is 15 volt as
15.
a
And now
current.
my
Yes.
question is, if it is 15 volt,
Hmm.
then you are the next stage is your 48. You are driving the battery for the with the buck converter, that is the generating the solar module.
No,
Which
buck converter driver generates the gate pulses. That gate pulses you are giving to
PWM.
yes, the gate pulses means it's a PWM. That will be feeding to the
PWM.
power circuit switch. Then power
Okay. So
circuit,
that switch
there
is
is
only
a
required
resistive load.
10 to 15 volt amplitude, not more than that.
That is your PWM voltage range. Am I right?
Range. Okay.
Yes.
Now
Hmm.
you can modulate that according to your need. Now my
Yes.
question is, when you are switching your speed, that is Arduino 16 megahertz is sufficient, or it because your square pulse it may not be coming because of this propagation delay or kind of thing, gate delay. So in that case, may we convert it to any other high-end, maybe Arduino or 240 megahertz? I think 16 megahertz. There is one Arduino Uno something. The number is I forgotten, but there is also 240 megahertz pulse. So may we use that? One question is that then my target is to only you are designing this buck converter for PWM generation.
Yes, this is a demonstration. In the demonstration, we are showing that how to generate the pulse, and after getting the pulse, we are feeding that pulse to the power circuit, and how the output. We are giving 20 volt as an input and 50% duty cycle. We are getting in open loop. Okay, so in open loop, and how the 10 volt is coming. And main thing is that how the fabrication's done and all those things. Everything
Mainly
will be
focused we
demonstrated.
are in PCB design mainly.
Exactly, yes, and how the basic things are there, because in this course different types, and some of the participants they want to know how to generate the PCB, how to develop the PCB, and how the entire thing will be carried over, right? Because all the converters are designed in our lab itself. Okay,
Yes.
so from the crash level to up to testing level. Okay, and the product after that prototype design. Okay, so
Now
that's
my
why
question is,
Hmm.
my question is, if there is any converter that has to be decided at real time. So if data is changing and we require to have our pulse with changing required at real time, then any kind of design there is, or it is only for PCB only, with a particular specific converter you have taken and it is implemented in PCB. Is it?
Yes, yes. Here only we have designed that internally back converter and using one of the one of the switch, and there was using the output, and that's it for this study only. Okay, and you are changing. You are asking that the closed loop operations. I think so, indirect way. So the closed loop operation is not going in this case. Okay, and yesterday evening they have demonstrated the real-time operations. If the YouTube link is already available, you can see they have demonstrated the integrated system. You can also see where the data are varying and how those things are handling power. Okay, all those things. So you can check it for the YouTube video link. Again, I'll share. Okay, so you can check it from there also. Okay, thank you.
Now Then one of my question is you
Madam,
yes,
yes. Because we are going to almost, our time was from 11, so it is 11:10. So, in next
There
session,
is
again, we are
there is
taking the
another
question. Definitely. So again, we'll take a lot of again questions, question answering session. There will be there. You can also ask. You can write the question. You can, because in our lab, all are demonstrating. Okay. So next session you can also ask the same question. You please note it down. We'll answer all those things. Okay. Let us start the next session.
Next
Then
session.
we'll answer the end of the next session. Okay, madam.
Okay.
Okay. Thank you. Jaidev, are you ready? Okay, so we are going to conclude our fourth session. Okay, so thank you, Shashak.
Thank you, sir. Yeah. Thank you, everyone.
Jaidev, am I audible from your end? Jaidev, can we start now?
Yes, sir. My screen is visible, right?
Yes, your screen is visible.
Okay, sir.
Okay, so good morning. So we are 1 minute. 1 minute. So very good morning. Now we are going to start our session 5. Okay, that session will be discussed by Jaidev Meher. He is a PhD scholar, senior PhD scholar in our department. He is going to deliver his presentation on different application and design for integrated multi-input converter for DC microgrid application as well as DAV converter, their switching techniques based on that. Okay, Jaidev, over to you. You please carry on.
Thank you, sir. Good morning, everyone. In this session, we will discuss about the designing and application of integrated multi-port converter, uh, which can integrate PB, pico hydro, and a battery, uh, and also supplying DC load along with the AC load. And between, we'll discuss about the DAV converter design also and its different switching technique. In this session, I will go through all this content. Let's start from the introduction. Why we are now more focused on the uh, multi-port converter or integrated multi-port converter. As we know, the need for sustainable energy has driven interest in renewable sources like solar, wind, tidal, biomass, hydro plant. It's a alternative to the fossil fuel. Because of we are more focused now, we are more focused on clean energy. That's we are more focusing on the renewable sources, how you will use efficiently. The renewable energy usage grow in last decade. We'll see the renewable energy grow very rapidly. With this, we need to integrate more than one renewable source in a single converter. That will become very essential because some of the renewable energy like PV, wind, these are intermittent in nature. Like PV depends on the solar irradiance. Wind is depend on the wind energy system is depend on the wind flow. And like pico water, if we take the hydropower plant, it's depend on the rain and the water flow. So these are not in our hand. So what you do to eradicate this problem, so we do what we do. We will integrate more than one sources, so that if one source is unable to supply the sufficient power, then other sources will supply the demand. This configuration in time we'll discuss about the one particular configuration that will be integrated multi-port converter. You can say this converter will supply uh, it has some advantages over the non-isolated or single multi-port converter. Like it has multiple power channels, independent power flow, inherent voltage boosting, and it can support sub-switching that can help in achieve maximum efficiency. Because of this intermittent nature of renewable sources, we are integrating more than one sources. But integrating more than one sources is a very challenging part also, because power managing between the sources and the converter, exact design of the converter became the very essential. If your converter design and efficient power management is not there, then enhancing the stability is very difficult and reliability of power supply also very difficult. So to achieve all these things, we need efficient or effective energy management and efficient converter design. With this, we can achieve uninterrupted power supply to the load, optimizing the use of available renewable sources, and increase the stability and reliability of the power system. Then the objective of this session will modeling and design of different converters that are used to integrate all the sources, and successfully will integrate PV, pico hydro, and energy storage system, and that can supply DC load as well as the AC load. And we'll implement some design and implement some control algorithm to stabilize the DC link voltage. And later we'll discuss about the DC DAV converter design and some modulation technique. How different modulation technique will help the DAV converter to achieve its optimum performance. Coming to the block diagram of the system, this figure represent the overall block diagram of the system that we have designed. Here we have used PV and pico hydro as sources and battery to stabilize the DC link voltage. We cannot connect directly sources into the DC link because all the sources, their output power and output voltage are different. So we need a common point to integrate all the sources, or you can connect reconnect parallelly. So to do that, we need some interfacing converter. Some we need DC-DC converter, sometime it will be AC to DC converter. Like as a PV is a solar PV is a DC power output sources. We need a DC-DC interfacing converter. We can use buck boost, a buck boost or a SEPIC converter. Here we are using SEPIC converter. Why you are using SEPIC converter? We'll discuss this later. And for a pico hydro, the output of the pico hydro is a AC quantity. So we need to convert into DC. Then or either it is stepping down or stepping up. It depends on the your system, energy system. So we are uh, designing this at the low DC link voltage around 220. That's why we need here a buck converter. So after converting AC to DC quantity, then we'll step down the DC voltage to a required DC link voltage, and we'll integrate this to DC link. Then for battery, these two PV and pico hydro, these two sources are unidirectional. So we need converter that can supply that will have unidirectional power flow capability. We don't need power directional capability, but in battery we need bidirectional converter, because the battery purpose is to stabilize the DC link voltage. So whenever it is needed, it can supply the uh, energy to the DC link voltage to stabilize the voltage. And whenever the DC link power is more, then it can extract from the DC link so that the voltage will remain at the limited, or the DC link voltage remain constant. Coming to the DC load side, we are using DC load as well as the AC load. DC load we can connect directly to the DC link. For the AC load, we need an inverter, like which can here we are using a 3-phase inverter, which is operated at 180 degree mode. we are not using as PWM or something to make it more smoother. For the basic purpose and for the conversion purpose and make it too simple, we are using only 180-degree mode. This feature have some inherent advantages compared to the others, like a different power flow channel, as the individual or a particular converter is assigned to a particular sources, the power flow path from the input to the output is different for different source. Means whenever one source is supplying through or supplying power to the load, then others at the same time the other source can also supply. And though there is no cross link between the one source to other source, you can say independent power flow path for improved power management. Whenever you go for the power management, so this point is very much necessary to should have independent power flow path. If let's see, if one converter is connected to the two sources, means one switch is responsible for the two source to extract power from input to output. Then at a particular time, only one of source is able to deliver the power, and the trace upon the switch also increases. So for the high power rating, that configuration is good for the low power rating. For the high power rating, we need the individual converter to integrate the different sources. And here we are using DAV converter to integrate the battery or storage system. We can use buck boost converter also, bidirectional buck boost converter, but we are intentionally using DAV converter because the DAV converter have inherent some advantages over the bidirectional buck boost converter. It can, if you used bidirectional buck boost converter, the your DC link voltage will be fixed. Once your converter is designed, then your DC link voltage is fixed and your switching range is limited. Means you can say from the input to output voltage range will be limited with the switching range. That means your duty cycle. But in this case, what happened as the DAV converter is consists of a high frequency transformer. So secondary side we can use multiple terminals at multiple voltage level. So for this particular design, we can have multiple DC link voltage to integrate. Means you are designing now it is 220 volt. In future you are planning for increasing to 400 volt. At that time also that single converter and same transformer uh, will help to integrate the battery also.
Sir, one question.
Yes.
Hello. Can DAB is used for multi-port or for if more than voltage for different rating? Is
More
multi-port
than
or
voltage means
one
and
volt?
it has a one transformer now. So
Yes, sir.
you can have a tapping at secondary side. Means
Okay.
you are giving 48 volt, your tapping will be 110 or 220 and 400 also, according to your transformer design. But you cannot use at a time at a different DC link. If you are
Yes, yes.
using
Okay.
at 220 volt, you can use only 220. And later,
Okay.
if you want to use that 400, up to 400 you can use. That doesn't mean you are using 401 DC link and 220 as one DC link. That
But
will be
at one time only we can use only 1 volt. No?
at
Okay.
one time you can
Hello. Hello. Hello.
Hello. Anything happened? I'm not hearing any.
Yes, ma'am, maybe disconnected. Jadip Mer, sir, maybe disconnected.
From your part, no? Is from your part?
No, no, ma'am, I'm also attendee. Maybe from organizer side.
The speaker has somehow disconnected.
Yes, yes, ma'am. Yes, ma'am.
Am I audible now?
Yes, sir. Yes, sir.
Yes, sir.
Okay, sir. Thank you. Yes. As you discussed in case scenario 1, the power coming from the PV, it fed to the DC link voltage through the peak converter. And that DC, from the DC link, we can supply both.
Not video.
Sir, your screen is not
Slack,
visible.
Slack.
Sir, your screen share has stopped, sir.
Okay, sir. Let me check once. Is it visible now?
Yes, sir.
Yes, sir. Yes,
Yes,
sir.
yes. Now it's visible.
It's visible, but not in full screen mode. Yeah, now it is.
Actually, I have a question.
Yes, yes, please.
Actually, like, why have you used like bipolar DC link? Like, mostly, like, we can see that seen that monopolar DC link has been used. If you can explain,
Means
please.
bipolar DC link means not bipolar. Actually, it's I am showing the positive and negative terminal only. DC link na or DC supply. It's like positive terminal and negative terminal. That's connection part will be clear so that I have shown that positive and negative. It doesn't mean bipolar DC link.
Okay, thank you.
Okay, coming to the case scenario 1, when PV is available, the PV only supply the DC link voltage, DC link, and from the DC link will supply the load, both AC and DC load, and also charging the battery. Here in this case, we'll see the switching sequence. In the switching sequence, for charging the battery, the primary side should lead the secondary side voltage. You can see S5 and S8 each leading compared to the S1 and S4. We'll discuss this switching sequence in the DAV converter. Only discuss the DAV individually. We'll discuss how this leading and lagging will vary according to the power supply. We'll discuss this one. For now, we can see the switching. But in this case, when you integrate the multiple converter, you need to consider one thing, that all the switches, those are connected to the source, should be at the same frequency. Here you are using 20 kilohertz to trigger all the switches. All the frequency are the same except the inverter. Those are on 50 kilohertz only. Sorry, 50 hertz only. Coming to the case scenario 2, here both the sources, if you plot the circuit diagram or connecting all the switches and sources, it will looks like this. And PB and Pico hydro both are supplying the DC link and the battery. In this case, the three-phase supply first converted to the DC, that will be one pulsating. That's how you use a capacitor to smooth it out. Then step down to the required DC link voltage. And from the PV, that's a peak converter used to extract the maximum power, and that fed to the DC link. And from the DC link, we are supplying the load and the battery. Coming to the case scenario 3, in this case, the PV is not available till, but the Pico hydro is connected. This will supply, it will be sufficient for supply the load and the battery charging. In case 4, when all the sources are not sufficient to supply the load, at that time battery can support to meet the demand. At that time, the switching of this battery will see the S1 and the S4. S1 and S4 each leading, means secondary side is leading in the to the primary side switching voltage. At that time, the power is supplying from secondary to the primary, and it will supply the both the load AC and DC. Coming to the modeling of the SEPIC converter, as we know, this SEPIC converter, it consists of two inductor. To designing these two inductor is very crucial. Why use the SEPIC converter, not the normal buck or boost converter? It has some inherent advantages over the PV system. It can handle a wide range of input voltage, make it ideal for variable solar condition. Means we know in a single day, the solar irradiation is changing. The level is power generation level also changing. At all the changing of solar irradiance, the power level also different. At all the power level, to track the maximum power, means to extract the maximum power from that low and high solar irradiance, we need a converter that can have a large voltage range area, means that can operate in a large voltage range area. Means sometime it will be buck the voltage, and means it can go up to the less than the 0.5 duty ratio, and sometime it can go above the 0.5 duty ratio, so that it can step sometime and it can step down or step up also. With both the cases, as this converter can support both the cases, so of tracking maximum power at all the irradiance value is easy compared to the normal buck or boost converter. But designing this parameter LS1 and LS2 is very crucial for this operation. So how we design it? So first, what we did, we actually basically use the equation 2 that gives the of inductor in terms of ripple inductor current and the voltage. Once we decide the output voltage and the input voltage, means our solar system solar module is known to us, and the DC link power DC link voltage is known to us. So we know the input and output voltage are fixed. Then the switching frequency, you have to decide a switching frequency at which you want to operate. Means if you are going to implement this system in the hardware, so you have to consider the hardware specification of the switch also. And you have limited into the simulation, so you can go to very high frequency, so that your inductance value will be less. For the hardware, if you want to experimentally, then that choosing the right frequency is very important, because all the components, mostly the whatever we are using IGBT modules from Semicron, those are operate a maximum frequency of 20 kilohertz. So what we did, we designed this system to operate up to the 20 kilohertz. So we choose in between 10 to not less than, not very less and not the towards the maximum. So we choose in between. It's around a 15 kilohertz we choose frequency, and we design all the inductor value. So once you know the input voltage, your frequency, then you have to find the uh, ripple inductor current. How do you do? So ripple inductor current, what you do? You choose a percentage of the current as a LS1. LS1 is connected to the source. So source current, the how much percentage of a source current will be your ripple current, that you have to assume. Normally we choose around 20%. For the safer side, we in design purpose in hardware also, we choose around 20% of the average current, and we decide the del IL value and the D value. D value also fixed once H, your input and output voltage are fixed, and D also fixed. So you can find L value. That L will be the inductor will be your minimum inductance, so that your converter will operate at a continuous conduction mode. So you need to take more than that inductance value. Similarly for the capacitance also. For capacitance case, what you do, you choose a del VC, means your output percentage. Normally what you do, we choose around 3 to 5% of the uh, average voltage, and we design that as capacitance value. That again, that capacitance is your minimum value, so you have to normally will take 1.5 to 2 times of the design value. So in this way, we'll find the L and C value. Once we'll check in the open mode, then we'll connect the PV, and again, then we integrate into the DC link. Coming to the buck converter, similar way, we keep in mind what type of system we are going to integrate with this buck converter. For that, we take the machine rating, how much rating machine we available in the lab, and compared to taking in mind, keeping in mind that voltage will decide the of V naught. V naught is your DC link voltage that will connected that will be connect in your output side of the buck converter. So in this case also, we will decide that ripple inductor current del ILB, that is also 20%. We take 20%. Maximum we can go up to the 30%, but we will take around 20%. And the same for the del V naught, a ripple voltage plus the capacitor. That will also take 3 to 5% of the output, average output of the system. In this case, we will design the inductance value and capacitance value for the buck converter also. Coming to the modeling of DAB converter, as you know, we have used DAB converter compared to the normal buck boost converter. It has so much advantages. Along with the advantages, it has some complexity also. I can give you a brief about the DAB converter. DAB converter nothing but it consists of two full bridge converter connected with a high frequency transformer, and all the switches are operated at 50% duty ratio. And how the power will transfer? The power will transfer from one terminal to different terminals, means from input or from output to input. It depends on the only phase shift between the bridge voltages. Means transformer, if you find the voltage across the transformer, that is the bridge voltage. That bridge voltage phase difference from primary to secondary that will only decide the power transfer from any side. Once your inductor is fixed, means once you design the TAV converter, your inductance value is fixed. So only the deciding factor is your phase difference. And at one phase difference is plus minus 90 degree. At that time, the TAV converter can transfer the maximum power from one end to other end. If you simplify this circuit, figure 5 will simplify, then figure 6 will represent the exact equivalent circuit of the DAB converter, where you will see two sources are connected through a inductor only. So phase shift between the two sources will transfer or will monitor the uh, power level, how much power you want to transfer. That will be decided by the only phase shift. It has some inherent advantage compared to the buck boost converter. It's provide high efficiency bidirectional power flow. Means your bidirectional power flow is very efficient. You just convert, you just monitor or change one parameter. Your bidirectional power will be of flow. Means if you want to supply, you want to transfer power from input to output then you want to transfer power from primary to secondary, then primary voltage should be leading to the secondary voltage. And similarly, if you want to transfer the power from secondary to primary, then your secondary should lead the primary. Means you just change the phase shift from the primary to secondary bridge voltage, from lagging to leading or leading to lagging. That's it. From that only you can transfer the power from both end. Means the power transfer become very much efficient. That's why
Sir,
the
one
DAB
point is that condition
yes,
should be 90 degrees or plus or minus 90 from primary to secondary and secondary to primary.
yeah, plus or minus 90 means plus 90 means is converting transferring from one end to different other end, and minus 90 means from other end to this end.
Thank you.
Like
Thank
that, that's why we have mentioned plus minus 90.
Sir, as you have shown in the cases, last
Mhm.
case you have discussed,
Yes.
when all the sources, when the load required more than the generating power. This DAB
Yes.
is working from secondary to primary side, na?
Yes, sir.
At that time, we have to change the phase shift, na, in the program.
You have to change the phase shift from lagging, leading, whatever earlier, you have to reverse the phase
Means
shift.
secondary will be leading and primary will be lagging.
Yes, sir.
Okay, sir. And sir, the all the switches, the second point, 50 for asymmetric duty cycle duty ratio, it may be different, na? It may be 40%, 30%. This is for asymmetric duty. Hello. Hello. Hello.
I think Sar has been disconnected.